All right, we're online. Welcome to all of you. I'm going to, all right, we'll make that little change. So today's lesson is 4.8. It's the last lesson in the chapter. Yesterday we had these optimization problems. They're kind of long, as you probably noticed. That's one of the reasons I only gave you 4. Nevertheless, we could at least take a look at one or maybe a couple of them. So I will now open it up to questions. Questions on 4.7, optimization. 31. Okay, Richard. 31. Okay, that was not an assigned question. But we could do that if you want. According to what I have here, if we yeah, here was the list for 4.7, 3, 5, 9, 11, 20, 23C, 33, 41, and 47. Oh, 33. We can do 33. All right, 33. Yeah, okay, 33 begins with this problem. Minimum surface area. A solid is formed by adjoining 2 hemispheres to the ends of a right circular cylinder. Morning, Rachel. We are taking a look at number 33 at the moment from lesson 4.7. So, okay, the total volume of the solid is 14 cubic centimeters. Find the radius of the cylinder that makes for the minimum surface area. All right, so this starts off with a given volume of 14 cubic centimeters. Half the difficulty here was coming up with a visualization. So you notice the drawing here. So the idea is you've got these half spheres mounted on the top and the bottom of a cylinder. Okay, so that's the picture there. And the volume of such a creature, well, this one's given, it's 14, but what's the volume formula for that? So you have to think about this a little bit. Because you have a hemisphere on both ends, you really have the volume of a sphere. Separated, but I mean, if you put them together, you'd have a sphere, and then you have a cylinder or a can. Okay, the volume of a sphere is 4/3 pi r cubed. That's this part right here on the right, 4/3 pi r cubed, and then the cylinder is the circumference times the height. Well, the circumference, I'm sorry, the area of the circle times the height. So pi r squared h. So, and they're telling us that's 14. So we have, here's our starting point, right? Let me get a red pen here. So this is our starting point right here. We've got the given volume of 14, and we set that equal to the volume for this object, which has half spheres on the end of it, and it's a can. Okay. So, I mean, we have 2 variables here. We've got R and we've got H. And as you know, we got to get down to 1 variable. So I decided, well, let's get rid of H. Let's get that. Let's get H in terms of R. So this top part here is me trying to get H by itself. So I left the pi r squared H on the right side. I subtracted the 4/3 pi r cubed. And then I divided both sides by pi r squared. That gave me this expression for H. All right, so now that I've got an expression for H, you notice over on the left side of this, it's strictly an R thing. Okay, so now I can get at the surface area. I mean, up until now, it's been a volume problem. But now we need to get into the surface area. So what's the surface area of this crazy thing? Well, again, it's 2 half spheres on top and bottom. the surface area of and so it becomes the surface area of a sphere when you put them together. And the surface area of a sphere is pi r squared. I'm sorry, 4 pi r squared. That's this part right here. And the surface area of a cylinder is the circumference times the height. Well, the circumference is 2 pi r. So 2 pi r times the height. And remember, I just figured this one out a few seconds ago. That was from the top. This thing up here. All right. So I know this looks a little bit messy, but now it's time to try to simplify this a little bit. So what I did is so I have 2 pi r times this quantity. So I multiplied out the distributive property. So 2 pi r times -4/3 is -8/3 pi r squared. 2 pi r times 14 pi r squared. We get 2 times 14 is 28. The pi and the r cancel, and you just have an r left on the bottom. All right. Actually, I could have started from there, but I went one more step before I took the derivative. And that is, I was able to take an r squared out of these first two terms here. So 4 pi minus 8/3 pi quantity times r squared plus 28, and I rewrote 28 over r as 28r to the -1. Now, let's take the derivative. Remember, the goal now is to minimize the perimeter. So that's going to happen when the first derivative is 0. So the first derivative, all right. Well, this whole thing in parentheses right here, this whole thing is, the parentheses part, let me try that again. We'll undo that. So this part right here is nothing more than a constant, right? 4 is a constant, pi is a constant, 8/3 is a constant, and pi. So this is just nothing more than a constant. And when you take a constant times something r squared, the derivative is, 2 times that. So this is 2 out here, and then reduce the power on r by 1. Well, 2 times 4 pi minus 8. This can be combined. And then over here, take a derivative of 28r to the -1, -28 r to the -2, and you reduce the power by 1. 8 pi minus, so this is 8 pi minus what? 5 1/3 pi? So it's like 24 pi over 3 minus 16 pi over 3 is 8 pi over 3. Okay, so that's just a simplification. All right, so there's my derivative, and now it's time to set the derivative equal to 0. All right, I added 28 over r squared to both sides. And then from, in this next step, I multiplied both sides by r squared. That got rid of this denominator over here. And when you multiply r squared times r, you get r cubed. So anyway, we can keep going here until, well, it's not easy, but you can just take the cube root of both sides. Well, the cube root of 28 over 8/3 pi, well, that you can hack out in your calculator. It turns out to be 1.5 centimeters. So that would be what number 33 looks like. So plan. The problem was we had to go from volume, then we had to go to surface area, so you had to know some formulas. You also had this problem of visualizing things, so I had to make a drawing. And then the other problem was, finally you got to get, so the end problem is minimize the surface area. So you got to get a surface area formula, plug in the specifics, take the derivative, set it equal to 0, and solve. Summary of Welcome, Jen. I don't know when you joined, but we were just going through number 33 from the problems from yesterday. Is there another question from yesterday you want to look at? 23C, okay. Yeah, so here's the problem in the book, in the drawing. Minimum length and minimum area. A right triangle is formed, as shown in the picture. A right triangle is formed in the first quadrant by the x and the y axes and a line through the point 1, 2. So you can see the point 1, 2 up here, and you can see that, you know, it's got the x-axis and the y-axis, and it forms a triangle, which is this pink thing in the picture. All right, so we know it goes through point 1, 2. Well, where did the book get this x comma 0? Well, we know it. I mean, it's on the x-axis, this point down here, so we know it's got to have a y-coordinate of 0, and we don't know its x-coordinate, so let's call it x0. Likewise, up here, we know it hits the y-axis. We don't know at what point, but we know it's got an x-coordinate of 0. So we've got these 3 points. All right. Write the length L of the hypotenuse as a function of x. So that's step 1. How can we get an equation? And how can we get a distance formula for these? Okay, so now we come back over here. So here's my picture of the same thing. The first thing I decided is, well, we've got what I call slope 1 and slope 2. Slope 1 is, I don't know, but slope 1 is this point and this point, the slope between those two. And then when you do slope 2, that's between this point and this point. Okay, well, since they're on the same line, don't they have to be the same slopes? So that's how I began. So slope 1, you know, y minus 2 over 0 minus 1. It's just y2 minus y1 over x2 minus x1, which gives me this. Okay? Slope 2, again, I did between these 2 points, gives me this. And of course, because they're of the same line, that means those 2 slopes must be equal. So I set them equal. You can then, because you have 2 fractions equal to each other, you can cross multiply. Top left times bottom right equals bottom left times top right. And then I just multiplied both sides by, I divided both sides by 1 minus x. Grab this so we can move it up. All right. And then I added 2 to both sides, and I got what's in blue right here. So just the blue ink part. And then I wanted to get this 2 connected, so I got a common denominator by multiplying top and bottom by 1. Anyway, finally, here's my equation for that line. All right. So now that I know that, let me think here. I guess I didn't really, anyway, I did that. And then I jumped right to C. Okay, and C says, find what are x and y so that this thing has the smallest possible area. That's this part on the bottom here. Okay? All right. So What is the area of a triangle? Base times height divided by 2. Base times height divided by 2. Base, another name for the base down here is x, right? X, because that's how far it is from here to here. It's x times the height, and the height is the y coordinate, okay? And then base times height divided by 2. So what's my base? X. What's my height? Well, I just figured it out. It's y. It's this expression right here. Negative 2x over 1 base times height divided by 2. Okay, then just getting that together, it looks like this. And of course, I can cancel 2's. So here is my function. All right, my function for the area of that. It all came from the area formula. Okay, so now I can take the derivative. So then I did a quotient rule. Denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. Okay, simplifying, I got it down to over here with the common denominator. And then I could set this equal to 0. When does an algebraic fraction equal 0? When the numerator is 0. So that's what this is. The numerator is set equal to 0. I added 2x to both sides, and I was able to factor that. X squared minus 2x equals 0. I didn't write the answer down, but you can see it. There are actually two answers, right? X is 0, and x could also be 2. Now, x of 0 makes no sense, because if you go back to the picture, what happens if I make x 0? Well, then this triangle is gone. It just collapsed. So that can't be it. But the other one, there's your solution. When x is 2, when this is a 2 point, 2 comma 0, you will have a minimum area. Again, kind of long and drawn out, but there's a couple of the problems from our last assignment. Okay, we better anybody have a follow-up question on either of those two we looked at today? Let's get started on lesson 4.8. This is called differentials. Differentials. And differentials, I mean, there's nothing new here. Differentials are kind of taking a derivative apart and looking at different pieces of it to help us make an approximation. Remember when we used Newton's method to find an approximate place where a curve crosses the x-axis? Well, this is somewhat similar to that. It uses the same kind of thing to find an approximation. Okay, so you can see the objectives here. Understand the concept. We all know what a tangent line is. And we're going to compare. Yeah, I guess that's not going to make a lot of sense until we dive into it. Okay, so the book encourages us to first do an exploration. Okay? And the concept here is use a graphing utility and graph the I'm going to graph this thing. We're going to graph that, and then in the same viewing window, graph the tangent line to the graph so the tangent line at the point 1, 1. Okay, so we need to do a little bit of algebra here. I mean, very calculus. Let's just do it real quickly. So the function is x squared. What's the derivative? Very easy derivative. Okay, now we got to do it at the point 1, 1. So what's the derivative at 1? Of course, that's just 2 times 1, or 2. So what's the equation of the tangent line at that point 1, 1? Well, we already know the slope is 2. And then we got to do it at the point 1, 1. So you can see that b would equal -1. So that the tangent line is y equals 2x minus 1. Okay? So now now that we've done that work, let's quickly go to Desmos and let's see what that looks like. So in Desmos, first we're going to do x squared. We all know what that looks like. That's a good old parabola sitting on the origin. Okay, and now what we did, we need to do our tangent line 2x minus 1. So you can see that, and of course, what's the point we're looking at? 1, 1. So right there, you see how the green tangent line is just barely kissing the x squared graph. All right. Now, as I zoom in closer, so what do you think? That green line, is that a pretty good approximation for what the red curve is doing? Yeah, the closer you go, I mean, could I use that green line to figure out the value on the red? Yeah, it's a pretty, it's not perfect. And when you get away from that point, you can see it parts. Because, of course, the original function is a curve and the tangent line is a straight line. So they go apart. But when you're near the point 1, 1, right there, I mean, it's really, if you're in this vicinity, it's going to really be close. Well, that's the idea of using a tangent line approximation. All right. So now let's go back. So tangent line approximations. Yeah, you can see it talks about Newton's method. Remember, we used that to find where a line crossed the x-axis. In this section, it says we will study other situations in which the graph can be approximated by the straight line because it's so close. And here's what it comes down to right here. This is what we have here is this will give us the height of a point at any value c. So in other words, if I wanted to find, let me just go back here. If I wanted to go back and find the height of this graph at, let's say, 1.2, so that would be right here. Okay. Well, supposed to be. I'm sorry, at 1.2, we're up here. At 1.1, here we go. At 1.1, will the green line give me a pretty good approximation for the height on the red? Yeah, you can see that the red curve and the green line are so close together, it's going to give me a pretty good approximation. Okay, so C in this case is 1.1. All right. So if we find, so we've got the equation. Can we find f at 1.1? Sure. Plug it into the function. What's 1.1 squared? All right. And then we're going to add to that to get the part where the curvature parts a little bit. We're going to take the derivative times the quantity x minus c. That'll give you a pretty good approximation. All right, so let's do an example. You can see our curve. Well, I'm trying to make this as big as possible, but yet not have it go off the screen. There we go. So our curve is y is up there on the top, 1 plus sine x, and we want to find the tangent line approximation at the point 0, 1. So if you look at the picture here, the black is the curve, and the point 0, 1 is right here. You can see we're right there. And then it says, all right, so anyway, what's the derivative of 1 plus sine? The derivative of 1 is nothing. The derivative of the sine is the cosine. So here's our derivative. All right, now, if you look at the top of the page, I copied that equation up there, way up on the top, this thing up here. And here they did it. So of the function, what's the function at 0? Okay, so look at the function now. What's the sine of 0? The sine of 0 is 0, right? And 1 plus 0 is 1. So there's that one. What's the derivative at 0? Well, here's the derivative. What's the cosine of 0? 1. And then times the quantity x minus 0. Why 0? Because we're trying to do it at, the point 0, 1. Well, this is simplified to 1 plus x. So in other words, what we just came up with, this is the tangent line approximation. And you can see it in the graph here. The graph, the function, 1 plus sine, is in black. And 1 plus x, which we just figured out, is this blue line right here. And you can see what? Within this range, it's really close. It's really close to the graph, and therefore should provide us with pretty good approximations. You're probably thinking, well, we know how to do derivatives. Why do we need an approximation? I would agree with that. But yeah, this approximation method is important for other things. Okay. So let's take a look at another one. This time we're going to do a table. And this example says we're going to compare something called delta y and delta y and dy. Okay. So this is where differentials come in. When you take a derivative, dy dx, okay, that equals what we would, yeah. Here, it's a little bit hard to talk about. Let's take the equation x squared. Okay, so I'm going to just find some space here. Up here we'll do it. All right. And let me get blue here. All right. So y equals x squared. Okay. We could say, now let's take the derivative of both sides. dy dx equals 2x. Now I'm purposely using Leibniz notation here because this lesson lends itself to that. So instead of saying y prime or f prime of x, I'm purposely using Leibniz notation. All right, now there's no problem here. Now this is dy dx is actually not dy divided by dx, and yet this kind of thinking works for this, because if you think of dx as a number and multiply both sides by dx, you could think of it this way. So I know this is a little bit strange, but this is called a differential. dy is equal to 2x dx. First time we've ever looked at it like that. All right, so that's dy. Now, delta y goes back to this concept. And that's where you say f of x plus delta x minus f of x, like the first part of a difference quotient. Okay. And we can actually, and that's equal to delta y. So delta y and dy are slightly different. Delta y is the height of the new point minus the height, it's just the change in y, the height. Dy is this derivative taken apart. So you're going to see us comparing dy and delta y. All right, now let me go back to where we were. Okay, so this time, again, we're taking the function x squared. And this time they tell you, find dy when x is 1 and dx is 0.01. Compare this with delta y. All right, so dy, remember we did dy. dy is 2x, that 2x dx. Remember that? 2x dx that we did right here. 2x dx. All right. So 2x I'm trying to find a best example. Trying to find the best way to explain this. So anyway, if you look at over here, I've got dy dx is another way to write the derivative of x. And if you multiply both sides by dx, you get dy equals the derivative times dx. So what is the derivative of x squared? It's 2x. Okay, you see that they did that right here. And now when you find dy, it's the derivative multiplied by dx, which in this case is 0.01. And you wind up with dy being, when you multiply it out, 0.02. Now when you do delta y, which is when you take f of x plus delta x minus f of x, you get, so you notice when we did dy, we got 0.02. When we did delta y, we got 0.0201. You see how they're extremely close? Dy is an approximation. Delta y is exact. So the point is they're so close together that you can use dy to find approximations. The picture here helps a little bit in that it's showing you kind of a picture of delta y is the real height from the first point to the second point, which is this delta y out here on the right. Dy is the same height, except it's using the straight line approximation. You see how it ends at the straight line there? And because there's a little tiny bit of separation between the straight line and the curve, they're going to be slightly different. But if you're close, if you don't take points too far away from where the tangent line is, there shouldn't be much of a difference. So if you look in the table, you can see the difference. Well, I tried to show it. So we've got the function x squared, okay, different values of x. And here's our tangent line approximation. Remember, we did that earlier. We found this approximation to be 2x minus 1. Remember, we did the work. Let me just remind you. Just got to find it. We did the work right here. That's how we found the 2x minus 1. So that was just using straight calculus. Find the equation of the tangent line. All right. So here's our approximation line, y, that's the tangent line equation. And you can see for different values of x, 0.5, we get these various numbers, okay? And you notice they're pretty doggone close to the function itself. You know, 0.81, 0.8, 0.98, 0.98, 1, 1, 1.0201, 1.02. See how close these two are to each other? Okay, therefore, it's a pretty good approximation tool. Okay, so let's just practice a little bit here. So first, let's find some differentials. You got the function x squared. The derivative of both sides, dy dx equals 2x. So thinking of dy dx as a ratio, get rid of the dx. Multiply both sides by dx. Differential, dy equals 2x dx. Okay, let's do a square root. Take the derivative of both sides. You know, this is x to the 1/2. It's 1/2 times x to the negative 1/2, which becomes 1 over 2 times the square root of x. What's the differential dy? Multiply both sides by dx. So really, to go from the derivative to the differential, that's easy. You just multiply both sides by dx. Here, 2 sine. Derivative, 2 cosine. Multiply both sides by dx. dy equals 2 cosine x dx. So this is not a big deal. Right? I mean, everybody can multiply both sides by dx. Okay. So, now, you know, I got to go grab something. I got to bring this back here. Yeah, I wanted to have this nearby. Here's that approximation. All right, so look at this. We're going to use differentials to approximate the square root of 16.5, which I know you think is totally stupid, because if I want to take the square root of 16.5, I can just plug in 16.5 and take the square root. I get that, but let's follow this line of reasoning to get an approximation for it. Okay, so we're going to use the function, the square root of x. Now, using this formula up here, what is it? It's f of c, okay? C is what? The square root of... So here's what we're going to do. We're going to say... I'm trying to think here. So what we're doing, yeah, let's think of it in this terms. F of x plus delta x. The function plus the derivative, okay, which we already know how to do. We're going to choose x to be 16 because it's close by 16.5 and it's nice and we know what the square root of that is. And dx, the bottom of the is the difference between where we are and where we need to be. 16, dx is 0.5. Okay, so here's how you can do the approximation. F of x plus delta x, the square root of 16.5 equals, okay, f at x, 16, square root of 16, plus the derivative there. The derivative is 1 over 2 times the square root of x, times dx, which is 0.5. So you see what's happening here. The square root of 16 we know, that's 4. 2 times the square root of 16 is 8. So we have 1/8 times 0.5, which is 1/2. Well, you work that all out and you get that for your approximation. Now, if you have a calculator handy, I'd urge you to do it with me. If we do this together, I guess I can do it on the screen here using... All right, so now if we do 16.5 and then do the square root, you see what you get. You get 4.062. You see how this is the exact, this thing I circled in red, that's the approximate. You see how, you can see how we got really close. Okay, so this is just an example. So we used for x, we used, you know, the nearby even square root 16. And for delta x, All right, how far were we off? 0.5. And then we were able to do this f of x plus delta x thing, and we came up with a pretty good approximation. You can also use it for estimation of error. So here we have, let's just read it. The measured radius of a ball bearing is 0.7 inch. You can see they've got it in a caliper up here, and they've got it measured for you. Estimate the propagated error in the volume of the ball bearing. All right. So how closely we've measured would greatly affect the volume of that, because to do the volume, as you can see, you have to do 4/3 times pi r cubed. So if r is off a little bit, when we cube it, it's going to be off. That's going to greatly exaggerate your error, correct? So, so first of all, I want to discuss the derivative here, okay? So we've got v equals 4/3 pi r cubed. What's the derivative? So if you look over to the right where I've written here, so you've got this v equals 4/3 pi r cubed. We want to take the derivative with respect to r. So on the left side, we have dv dr. And on the right side, power rule, 3 times 4/3 is 4. 4 pi r, reduce the power by 1 squared. Now, if you take this differential step, dv dr equals 4 pi r squared, multiply both sides by dr, and you get this expression. Down here on the bottom, you get 4 pi r squared dr is what dv is. And now, if we come back, that's what they were doing right here. Okay, to approximate the propagated error in volume, differentiate v to obtain. Okay, that's what we just did. All right. So now what's the radius? The radius given in the problem was 0.7. Plug it in. And dr, that was this thing up here on the top. The measurement is correct to within 0.01 of an inch. That's our dr, the differential in the radius. And when you solve all of that, you get, plus or minus 0.06 cubic inch. So the volume has a propagated error of approximately 0.06. Now, what would you say that error is? Too large or too small? And what you do is you divide that by the actual volume, okay? So you take that value and divide, and you find out it's only, It's about 4% error. Okay, so the point here is when you have an error in one thing, you plug it into a formula, it gets multiplied. And so differentials can be helpful in finding the percent of error. Okay, now for an assignment, I've got the assignment where, first of all, I changed it. So in your book or on the website, it's got all these numbers, and I've just changed it to 7 to 21 odd. So please note that, 7 to 21 odd. Over here, you'll see I've just asked you to do kind of the basics here. So number 7, the function is x cubed. They've given you the x value, and they've given you the differential value. Okay? Use the information to compare delta y and dy. Okay? So, as you know, to find, let's just review. How do you find dy? Oops, let me get my writing utensil. How do you find dy? Well, you take your function and that's y, and then you take the derivative, and then to find dy, you just multiply both sides by dx. So there's your dy, okay? And then to actually calculate dy, you could plug in this x value and this dx value. And you can just find the answer. Okay, what's delta y? To find delta y, okay, for that, you are trying to find f of x plus delta x minus f of x. Okay, so now for that, you're going to plug it, you're going to, so in this problem, what is that? F of, and then x is 1, and delta x is 0.1. 0.1, excuse me. And minus f of x. And then, so you're saying f of 1.1 minus f of 1. So now you just take, what's the original function? X cubed. So basically, just to wrap, I got to move this up a little bit. So now you're finding 1.1 cubed minus 1 cubed. And then you're going to compare, these two answers. When it comes to some of these later ones, the second part here, it says in numbers 11 to 24, find the differential dy. So there you're just trying to find dy. Okay? So, example 11. Take the derivative using Leibniz notation, and then multiply both sides by dx. So that's the kind of work you're going to be doing on that second section. So let me repeat again, it's kind of a different assignment here. You are supposed to be doing, I kind of completely started over here from what it says in your syllabus. 7 to 21, the odds. Just trying to get you guys used to taking these derivatives apart a little bit, and then using this as an approximation tool. It's important enough that the book decided we need to have an extra lesson. Questions? Anybody? Another beautiful day out there, huh? Sunshine is nice. All right, thank you. Good to see you. And I say see you. I got to at least see your name and get a couple questions here and there from you. It's always good to work with you guys. I will see you then on tomorrow. Thank you.